Last episode, we built one heatsink and simulated it by hand, and it took real effort. We set up the case, we meshed it, we set up the physics, solved post-processing. Every single step, we did it manually. Now, today, we run 15 of these simulations without touching the mouse at all. One command kicks off a whole bunch of simulations, and a table quietly fills itself in, one row per design. This is the episode where CFD stops being a point and click chore and becomes a program that runs itself. Quick map, episode 1 was the Y, episode 2 we built the baseline, our number to beat, a Q over V of 1.08. This episode, number 3, is the first real automation. We wrap OpenFOAM in Python and sweep each design knob to see how it behaves. It's the bridge to the smart search coming in episodes 4 and 5. So, we have 3 knobs we can turn: the number of fins, how thick each fin is, and how tall they are. The tempting move is to throw an optimizer at all 3 at once, but before that there's something simpler and smarter worth doing. We change one knob at a time and hold the other 2 fixed. Sweep the number of fins while thickness and height stay put. Then sweep thickness, then height. 5 values each. It's cheap intuition before the expensive search. It tells us which knobs actually matter and roughly which direction is better. 15 runs in total, and the whole point is we are going to let the computer do all 15 for us. Because we can't really say, for example, how tall a fin should be. It's all going to be automated. Everything I'm about to show you is on the GitHub repo, and I genuinely recommend cloning it and following along. This episode is meant to be reproducible. This right here is the GitHub repo, as you can see. If you want to copy or clone this particular repo, you can use this URL. What you would want to do is go to your terminal and type in this command. Once you do so, we will clone this repository, and you can essentially go through what the constituents of this folder actually are. You will see the 3 folders: the driver script, the OpenFOAM template, the environment file, and a setup script. First, the environment. All the host side Python, generating geometry, reading results, plotting, everything runs in one clean, reproducible Conda environment. Now, of course, if you don't have Conda yet, at least install mini Conda. It's the lightweight version, free, and it works the same on Mac, Linux, and Windows, the same. The whole environment is pinned in one file, environment.yml. This is the recipe, so to speak. We're using Python 3.11 plus numpy and pandas for the data, matplotlib for the plots, and 2 important ones: numpy-stl, which lets us build the heatsink geometry as an STL straight from Python, and optuna. This is the optimizer we'll use later. Pinning it in a file means anyone can recreate the exact same environment with just one command. The command, as you can see, is written right here in the terminal. And to make it active, you just activate that particular environment. You'll see the name in your prompt itself. And every Python command now runs against exactly the versions that I am using. There's no works on my machine. 2 more pieces, and I'll be honest about my setup so you can also adapt it. The heavy CFD, the meshing and solving, essentially runs in OpenFOAM 2506 on Linux. I run that inside a lightweight virtual machine using multipass or multipass, so it lives right alongside my Mac here. If you're already on Linux, you can skip this VM entirely and point the scripts at your local OpenFOAM itself. And the second point, I keep all the results, which really get big, on an external drive. There's a setup script that wires all that together once. It does 4 things. It takes the results folder on the drive, it shares that folder into the virtual machine so both sides can see it, it builds the Conda environment we just talked about, and finally it checks that OpenFOAM actually answers inside the VM. Run it once and you never have to think about it again. If all 4 steps come back green, you are ready to run simulations. Okay, the engine. Conceptually, it's a loop with 5 different moves, and it's worth seeing the shape before we even go to the code. 1. Python picks the parameters for this design, say 7 fins. 2. It sets up a fresh OpenFOAM case and generates the STL geometry for those exact numbers. 3. It ships that case to the virtual machine, which meshes it and solves it. 4. The results come back to the drive. 5. We pull out the heat dissipated Q and write one row to a spreadsheet. Then it just loops. Next design. Once this exists, running 15 cases is the same effort as running one. That loop is really 2 scripts talking to each other, and I want to walk through both because they are the reusable part. The first is the driver, optimize heatsink.py. It runs on the host and it has a handful of small, honest functions. Setup_case copies the template and patches the dictionaries for this design. Generate_stl turns the 3 numbers into a heatsink STL. Run_OpenFOAM hands the case to the VM. And extract_heat_flux reads the solved result and pulls out Q. The sweep command just calls these in a loop over whatever values you give it. And that's the command. The whole batch is one line. Sweep the variable nfin over 3, 5, 7, 9 and 11. The second script is the one that runs inside the VM, run-openfoam.sh. This is the actual CFD pipeline in order. BlockMesh builds the background grid, Surface Feature Extract picks the edges, Snappy Hex Mesh carves the mesh around the fins, Buoyant Simple Foam solves the flow and heat, and Foam to VTK exports it for viewing. Every stage checks itself. If meshing or solving fails, it says so and bails out cleanly instead of silently producing garbage. That last part matters a lot when you're running unattended. One practical detail. The data lives in 3 places on purpose: a staging area on the host, fast scratch space on the VM for the actual solve, and the external drive for the permanent copy. Meshing hammers the disk with thousands of tiny files, so you always want that happening on fast local storage, not a network share. Enough explanation, let's just run it. I'll kick off the fin count sweep here, starting all the way from 3 to 11. This would be 3, 5, 7, 9 and 11. So let's take a look at that. For each design, it patches the case, generates the STL, fires the solver off on the VM and waits. Each solve takes a few minutes, so I'll speed this up, but here's the satisfying part. Every time one finishes, a fresh row lands in results.csv. Number of fins, the volume, the heat dissipated, and Q over V computed and logged automatically. This is the whole pitch of the episode. 15 simulations, 0 clicks. Let's talk about that table here, because how the numbers get recorded is half the value here. Every single run across the whole project appends one row to the master file, results.csv. The columns are the design, fin thickness, number of fins, height. Then the outputs, the solid volume, the heat Q in watts, our efficiency number Q over V, and a status. That status column is important. It records whether the run was okay or failed, so nothing gets silently lost. For this episode, we ran 3 sweeps of 5 values, 15 designs, 13 solved cleanly, 2 failed. 9 fins at 2 millimeters and 3 millimeters fins, and that's fine. Real automation hits failures. The point is, it logs them, moves on, and doesn't crash the whole batch. So the payoff: 3 clean trends, all from real solves. Number of fins, more A is better. Q over V climbs the whole way from 0.9 at 3 fins up past 1.3 at 11. More fins, more surface area, more cooling per unit metal. Thickness, this is the big one. Thinner fins win hard. Going from 2 millimeters down to 1 takes Q over V from 1.08 all the way to 1.46. Our best single result so far. Why? The cooling surface barely changes with thickness, but the metal you spend does. Thinner fin, same heat, less volume. And height, taller helps, but with diminishing returns. It keeps climbing, but each extra millimeter buys less because the top of a tall fin is sitting in air that's already been warmed by the fin below it. Here's the punchline and the problem. Each of those sweeps found the best value of one knob, but only while other two sat at their defaults. Thin fins are great, but are 11 thin fins great? Tall and thin and many all at once? Is that a disaster or the jackpot? The sweeps can't really tell us because each one only ever walks a single edge of the design space. The real optimum is somewhere inside a specific combination that no single sweep ever visited. And we can't just grid search all combinations, that's hundreds of 8-minute solves, days of compute. So we need something smarter than just brute force. Something that learns from every run and decides what to try next. That's Bayesian optimization, and it's the whole next episode. All the code, the environment file, the exact commands, everything is on GitHub, link in the description there. Clone it, point it at your own geometry and let it run. Again, a shameless plug here, but if this was useful, subscribe so you don't miss the optimizer, and I'll see you in the next one. Keep your residuals low.